Welcome everyone. Nice to see all of you here. Should I be using this?
Yeah. Okay.
Yes, like this. Good. It doesn't correct for Greek accent, does it? Welcome everyone. So nice to be here. It's my pleasure to start the seminar series. The first talk with really brilliant scientist and the director of RMI in Spang. A little bit about AIFS and the seminar series. So AIFS is one of the 25 national AI institutes. This came from an presentation on Monday 2019. We were in the first cohort of 7 institutes that was introduced in 2020. We have been funded with $500 million, or just us, and more institutes are coming. The vision for the program has been on, hey, AI is important, it's here to stay, and will change our lives. How can we make sure that we stay ahead and we put the right efforts to make it better and the right guardrails and safeguards to make sure that it doesn't change our lives in a negative way. So there are 5 USDA institutes out of the 25 that are NSF and other agencies, and we are the only one that is focused on food systems. What is a food system? Well, we all consume food. Food comes from somewhere, and there is so many things that need to happen to start from a seed that will be planted, that will be processed, fruits will be harvested, processed, and then will go to consumer. So many things that need to happen. Question is, how can we make it better? Right now, it's very inefficient. And it is a lot of the things that we see, including like the labels you see in products, including what we know, what's in our food and what it does to our body, is from the 1970s. So the vision of the Institute is a healthier society and a more sustainable planet. And our mission is to bring the AI at the center of this. With that, we are starting our series. The series are with talks of people who are in the food system and they are applying AI, innovative AI in the food system, or the AI scientists and engineers, and they're having applications on the food system. And with that, I would like to welcome Farrell Smith, who is the chair of our board.
Thank you, Elias. It's a real honor to be able to help initiate this event. And we're really pleased to have Ned talk to us today. So Ned, during the past couple of decades, so 2 decades, thereabouts, I don't know the exact year, but at least the 2 past decades, Ned has taken a systems approach that is at least rare, if not unique, in terms of integrating techno-economic analyses of systems in the food system that Elias is talking about, along with life cycle analyses of those systems. And during this time, he's actually, his systems are the nexus of food, energy, and water, which are pretty fundamental from a societal grand challenges perspective. He's been embodying that here at UC Davis by the multidisciplinary approach of looking across everything from coffee to water resources to brewing waste streams to almonds, pistachios, et cetera, So a system of systems approaches with what we work with here. And he's also leads a really interesting effort on the food waste or food loss and waste collaborative. Did I get it right?
Nailed it.
Excellent. So the Food Waste and Loss Collaborative, which takes a systems view of this and works on specific projects. And then he also is the director of the Robert Mondavi Institute for Wine and Food Science, which connects the campus in this very multidisciplinary way across food and B&E and all the other departments and schools at the university and creates a communications fabric. And then the last comment that I wanted to make is that I've spent 30 years in the food sector, crossing the industry, government, and university boundaries, as well as foundations. And so the work that Ned is doing, that kind of systems work, is essential if we're going to solve grand challenges in this space. And what I've come to understand after 30 years is that if we don't actually put AI at the center of it, it's going to take too long for us to actually work our way through that data to get to those solutions. So it's a real pleasure to be able to work with people like Ned, who not only have the systems approach, but also bring this AI at the center approach and figuring out how to construct that architecture. So looking forward to hearing what you have to say. Thank you, Ned.
All right, thank you so much, Harold. Thank you, Elias. It's a pleasure to speak with everybody today. I think, Harold, you maybe just saved me my first slide, actually. I can actually pick up some time here. So today I'm talking about upcycling and creating a digital atlas of food and agricultural byproducts. Before we get to the AI, I actually want to kind of build the storyline a little bit here of why we're looking at this particular challenge the way we are. I think it's important to understand, how our work, sometimes we get into the weeds, we're looking at data and spreadsheets, but it's important to pop our heads up and ask, what is the purpose of this? How can this help create better food systems? So I want to start with that and then work our way into some of the research. As Harold mentioned, I'm an associate professor of food science and technology here on campus, the director of the Robert Mondavi Institute for Wine and Food Science, and the founding faculty member of the Food Loss and Waste Collaborative. I've also advised external to the university the Upcycled Food Association Standards Committee. So this is allowing us to think about how we might use byproducts or food processing co-products, not treat them as waste, but actually as ingredients or raw materials for new products. So that's an important topic that I'm going to spend quite a bit of time talking about today. And actually, this is one of those rare talks where I think I'm doing my job in all four of these roles at the same time. So it's a good use of my time. So food loss and waste, what are we talking about when we think about this issue? When I look at the food system and how it relates to different environmental systems like energy and water and waste and climate, food loss and waste always just rises to the top as this opportunity for us to do a lot better. Because you can talk about different irrigation techniques and becoming more efficient in our water supply and how we direct that towards food systems. All of that's important. But if we're still growing food that then we don't eat, the challenge remains. So if we can think about food loss and waste and developing solutions to keep some of that food in our food supply chain or use it as a raw material and not as a waste, we actually get to recover a lot of these wasted resources that currently are not providing any value whatsoever. So a recent study by EPA showed that 6.1% of our total national greenhouse gas emissions are associated with food loss and waste. 22% of all our freshwater use, 16% of our cropland, and 24% of our landfill waste. These are tremendous numbers. And on the one hand, you can sort of look at these numbers and get depressed and think about how awful all this stuff is. But I look at it exactly the other way, that there's a huge opportunity here. There's a lot of low-hanging fruit when the numbers are this big to actually make meaningful change relatively quickly. So where is food wasted across the food supply chain? It's wasted everywhere, or lost or wasted across the food supply chain. It's left behind on the farms. Sometimes that's because of weather, the quality of the crop, or perhaps the cost of the actual commodity drops below the cost of harvesting that commodity. So if the price of tomatoes drops, it might not be worth sending a crew through to the field to actually harvest. And that kind of thing happens. On the manufacturing side, it's often a co-product or byproduct is the terminology we use. So if you think about the salsa jar that you open, that was tomatoes that were chopped up, it's onions that were chopped up, and all of the skins, the tops, the bottoms, seeds, all that kind of stuff is a byproduct waste. Once we get to sort of the further end of the food supply chain, in the US, a lot of the waste is down at this side. So about 70% with consumer-facing businesses and homes. That's the food loss and waste that you guys experience when you eat, half your dinner at a restaurant because they've given you too much food. Or you buy too much food and then go on vacation and forget that you just bought all this food. It happens to all of us. I mean, no one is perfect in terms of this particular topic, but little behavior changes and learning about this and a little bit of education, we can all make a difference on the consumer side. What's interesting to me is the nature of the waste at the different parts of the food supply chain. It looks very different. If we look at the farm and we think about all those tomatoes that weren't harvested, if we want to try to get value out of that, we have to go get those tomatoes out of the field. That's expensive. It's kind of spread out. You have to have a picking crew. You have to have a way to move that material from point A to point B. On the other side of the food supply chain, it's in our homes. It's a mixture of waste. It's a mixture of food and packaging. It's really hard to get value out of that. It's spread out. It's heterogeneous. It's very low value. But here in the manufacturing sector, 13 million tons, it's centralized, it's consistent, and it's homogeneous. So that is a great opportunity for, I guess my title slide is a little mixed up there, but it says, ideal valorization opportunity, consistent, centralized, and homogeneous. There's a real opportunity here. And in fact, we've done a pretty good job in this space in the past because of these characteristics, we've often directed some of this to animal feed. So that's keeping this material indirectly still in the food supply chain. There's opportunities there. But I do think there's a lot more room to generate value at this part of the food supply chain. Another thing to consider is, what do we do with food loss and waste? How do we rank our solutions? So we know that the food loss and waste is different for different crops and at different parts of the food supply chain. The solutions are also different. So you can come across lots of different solutions: anaerobic digestion, turning that food material into bioenergy, and a soil amendment. That sounds great, but that actually might not be as great as donating that food, if it's still edible, to a food bank. There's a whole hierarchy of solutions, and the EPA just came out with this updated food waste scale that's backed by life cycle assessment. So understanding the environmental impact of all these solutions relative to one another. And always at the top is preventing food loss and waste in the first place. Then we go into donation and upcycling. And this is where I'm going to focus the talk today. Because this is such a high-level solution where we're actually getting value out of this material, there's a lot of opportunity to try to keep this in the food supply chain or treat some of these materials as medicines, pharmaceuticals, you name it. There's a lot of really valuable compounds in the food and agricultural byproducts. Going down the list, other solutions, just to let you know: feeding animals, leaving it unharvested, at least in that sense. The chemicals, the carbon, everything's going back into the soil. Composting, we're all familiar with. Anaerobic digestion is divided into two pieces, because on the one hand, you get some biogas when you do anaerobic digestion, but it depends on what you do with the material that's left over. If you use it as a soil amendment, it's more beneficial than just getting rid of that, the digestate that you've now produced and putting it in a landfill. You're not getting nearly as much value out of that, but that is what's happening in some situations. Finally, sending it to landfill or sending it down the drain, incinerating it, there's basically zero value solutions there with environmental costs. So I want to talk about three different sort of ways, frameworks for you guys to think about upcycling, and ways that I'm working on it or have worked on it in the past. This is one particular way of upcycling where you take the material and you use it directly as a food ingredient. Okay? You might have to dry it or mill it, but we're not extracting compounds out of it. We're just taking this material, realizing it might have a flavor profile, a beneficial nutritional profile, and putting it into a new food product. So a number of years ago, I had a group of undergraduate students. We charged them with this question. We said, we have a partner that runs a juicing company. They make really high quality juice that they sell out the front door, and they have all this material, this fiber that's going out the back door. Is there something we can do? Can we use this as an ingredient for food products? And it was a really fun year. I had the students for the whole year. They were in the food innovation lab, mixing all together crazy ideas. Some of them were delicious, some of them were not. But trial and error. But it allowed us to think about solutions. And all the food science students love to cook. I mean, they're excited. They have fun with that too. But this added dimension of trying to problem solve an environmental problem while also developing a recipe just got them excited like I've never really seen before. The story mattered. We all think about where our food comes from. We want to have some sort of narrative behind our food. It aligns with how we think about food culturally. And this was no different. It was really exciting to take something that was previously a problem and make it a delicious ingredient. So while they came up with lots of interesting products, the one that really they decided to focus on was what they called a mocha bite. It used almond pumace from almond milk that they were making on site at the juicing company and cold brew coffee grounds. They added pea protein, so plant-based protein, and it had a high level of protein, caffeine, and tasted great, and I made them deliver to my office every afternoon, just when I needed it, like 2 or 3 o'clock. But they hit all their nutritional guidelines. They got so excited about this product, they made 3 other flavors. I didn't even ask them to do that. They just wanted to do this. And by the end of the year, I actually had them enter the business competition on campus, and they won an award. They won $10,000 for the specific business competition of doing more with less, which is exactly what the design of this process was. They actually made enough of these mocha bites to share it at the Fancy Food Show in Sacramento. They were featured in the media. I mean, this was an incredible project. We did not set out to have these goals. I just wanted one tasty bite at the end of the year. But what happened was, again, this creativity, this excitement, this new way of looking at the food system really caught on with the students. So that's upcycling as an ingredient. Another way to think about things is, okay, let's take this broader systems perspective, as Harold was discussing before. What can we do broadly in the food system? How do we think about where food and food-related material goes now? Where could it go in the future? How do we think about this differently? A lot of our economy right now is a one-way ticket. We call it sort of a linear flow. So we extract a raw material, we make something, we consume it or use it, and dispose of it. It's a one-way ticket. But another way to think about things is more circular. How do we take our waste and use it to create something else? Can it be used again in the same system? Can it be used again in another system? So this is a different way of considering this potential problem. So if we think about grape pumice, and grape pumice is what's left over when we're making wine, of course. We're pressing the juice from the grapes, and we have a lot of the skins and seeds, sometimes stems left over. Is there any value in this material? Previously, we might dump it in a landfill. We might use it as compost, put it on the field, or we might give it to animals. All of these, as we saw in my food solutions hierarchy, they have varying benefits here and there. Actually, one study on UC Davis campus just found that grape pumice reduces methane emissions in cows when you add it to their feed. Great solution. So we maybe have been doing this a little bit in the past, but now we know there's added benefits. Or now we know that the cow might actually be able to eat more than we've given it. There's research that you can do still at all these sort of traditional pathways. But what are some new pathways we can consider? Extraction is a whole nother area that we haven't spent a lot of time figuring out what we can do with a lot of materials. Certainly there are many examples of extraction in the past. We've extracted whey protein from whey when you make cheese for a long time. We've used that material. It's in fact almost as valuable as the cheese in many cheese making operations. But what are some other compounds that we can get out of the food, especially these byproducts? So instead of going and getting raw material to get an extract, let's use some of this material that's already sitting around or considered low value. So in my department, there's a number of researchers who have worked in this area. This is not even comprehensive, but Alison Mitchell has worked on extracting phenolics and antioxidants from grape pumice. So these can be, compounds like anthocyanins. You can use it as a food dye. It's also good for you. We can track the benefits of these particular compounds for human health. Dr. Daniela Barile has worked with oligosaccharides. These are a really powerful prebiotic. This has been the core of her research for a number of years. They've already figured out how to use these particular oligosaccharides from grape pumice in chocolate bars. So this is kind of incredible that now we're linking together two of the greatest things we've ever invented, wine and chocolate, to create a new product that is actually in the marketplace now. We also have other researchers that are looking at proteins, lipids, you name it. We can think about what we can extract from this material. Proteins are really exciting right now. Of course, we're thinking about alternative proteins. There's a number of different pathways there. But if we can start to generate proteins from some of these waste pathways that we previously had, it's incredibly powerful. What we really want to avoid is that landfill option. Again, we don't necessarily have to use every material and extract every compound out of it. What we want to do is work with that hierarchy to see, in this particular situation with grape pumice, where can we get the most value? Where can we create the best benefit for society? And then let's work our way down from there to figure out what to do with the remaining material. Because extraction is not a waste management solution, it's a valorization solution. So you get some value, that's great, but you still have a lot of material left over. So we have to sort of combine these different approaches to come up with a full solution. That's why we call this the circular refinery model, where you sort of step down from an input to a number of different strategic outputs of declining value over time. So In another research project, I've worked with Chris Simmons. Chris Simmons has also done shared some of the upcycling work with me. But we've looked at anaerobic digestion. What scale of anaerobic digestion is a good match for different feedstocks? Is it always better to have a big centralized facility? Or does it make sense to have smaller modular facilities that we can deliver to sites at certain times of year and move them around? So we're asking questions like that in terms of what should the infrastructure look like, should look like to generate some of these benefits of bioenergy and soil amendments. So after you've generated the energy, you still have this material left over, as I showed you in the hierarchy. Let's make sure that that gets put back into the agricultural cycle and fully closes the loop of opportunity here with a biorefinery. Another potential solution that Dr. Simmons is working on that's quite interesting is biosolarization. This is using some of this material in a particular way when we apply it to the field. Add it to the field, add water, and cover it with a tarp. And the heat and the fermentation that takes place in the soil can displace some of the worst fumigants that we put into our food system. So this is a really incredible in terms of not just the health of the soil, but also the health of the workers who have to handle those materials if we don't come up with other solutions like this to displace some of these nasty chemicals that we currently use. There's lots of ways to be creative when we start thinking about these circular systems. The other piece you have to think about is that no one is an expert on this entire cycle. This is what we do very well at UC Davis, is that we connect the people who have a specialization in each of these linkages together to look at the system as a whole. Okay, now I'll get to the part that we're all focused on here, which is the Food and Ag Byproduct Digital Atlas. So when I present to you those frameworks of thinking, using upcycled ingredients in foods, you thinking towards what a circular economy might look like, we have to have the underlying information to decide what is the best pathway forward on any of these options. The problem with waste, or what's previously considered waste, is that we rarely have good data on this material. Every single processing plant out there can tell you exactly how much of their product they're making, but they might not tell you how much waste they're generating. They may know or not know, they may not want to share, but we're trying to get an understanding of how much of this material is available. What is it made of? When is it available? What is the value of some of the chemical compounds that is in this material? This is an entirely black box. So as much as people might want solutions, they don't have the information to really design and implement those solutions right now. So the goal of this particular project is to actually develop a database of food processing byproducts to help generate solutions on these valorization pathways. The process for this is really thinking about what are we generating here in California. Of course, we're starting in California, but we hope to expand this database nationally and potentially even internationally. Once we understand the systems, that gets a lot easier. So we select the top food items we have here in California. We've started with tomatoes. We've already made progress on wineries and grape pumace. And then we'll be moving into pomegranates, almonds, and pistachios in the near future. We're taking an approach where we're actually looking all the way from the farm through the manufacturing. We do want to understand what is left behind on the farm. That has been another black box historically, because if we think about it, every farmer knows exactly what they sold to the market. They do not know what's necessarily left behind in the field. So we're trying to get to the bottom of some of that data, and that's been something I've been working on for a number of years. Then we go to the processing plant and really try to understand a mass flow analysis. If we have this amount of input, how much product do we get, and how many byproducts, and of what types come out from that processing facility. Finally, what is in those different waste streams or byproducts, co-products? How do we extract it, and what is the commercial value of that material? There's a lot of puzzle pieces to put together for each of these systems, and they're highly complex, they're highly variable. So we need to leverage aspects of AI to start pulling this information together. If this was all just done just by graduate students and undergraduates, and they're doing a lot of it right now, it's going to take a very long time. But if we can start to search for patterns here, we can start to speed this up and scale it up faster than we could previously. So this is the key. It's AI as an accelerant to bring this data together in a much faster way than we could before. So here's what the actual mass flow looks like. I'm sorry this is small, but it is a complex system. If you just kind of zoom out and don't try to read everything, I can tell you that this is all the tomatoes that were planted in California. So the total amount of tons of tomatoes that would be generated just based on what's planted. We have an understanding of what is harvested versus unharvested. Then we have this separation of tomatoes that are going to tomato paste and canned tomatoes, either whole tomatoes or diced tomatoes. But all of these little pieces that are slicing off are waste streams of different chemical composition. Some are full tomatoes left in the field. Some are tomatoes that were green or moldy that came off the truck. Some of it is tomato water, which is what's left over after you evaporate the, you take the tomato water away from tomato paste. You have a lot of different tomato pumace that's pressed out of this material. There's lots of different waste streams. It's not just one, and we have to understand what would be the solutions for each of these. So if we think about what we started with, here are the products that we're ending with, okay? That's 26% of the mass of the tomatoes that was originally planted. That's the final product. So that means that 74% is a whole nother set of material that could be leveraged for some value. It's the majority of what is produced, not the minority. So there's a lot of different ways to think about this. Oh, I did want to highlight too that pumace is what I'm going to be talking about in the next few slides. Pumace is basically the skins and seeds from the tomato. When you kind of press all the juice out to make what's called the tomato water, that then you evaporate the water and you have the tomato paste. It's all the really fibrous material, mostly skins and seeds and some pulp. So we started looking at what is in this tomato pumace. Reviewed quite a few studies. So there's two main categories I have here: extraction via solvent methods and extraction via supercritical CO2. So we have a higher extraction rate of supercritical CO2, and this is in milligrams per grams. This allows us to connect the dots between, okay, I have this much pumace. I know I have maybe this much lycopene I can extract through these different technologies. So 560 tons using the solvent approach, 4,000 tons using a supercritical CO2. We looked up the value of lycopene and Sigma Aldrich. It's $105 per milligram. That would mean we have $60 trillion in lycopene in all the tomato pumace that we produce in California. Now, of course, the market for lycopene is not that big. The market for lycopene is 161 million. But this just gives you a sense of scale of what we're dealing with. I mean, I had to check the math on this like 3 times to make sure that this was a T and not a B or an M. So it's really amazing. It's like this treasure trove of particular chemicals if we can extract these things. Now, what we haven't done yet, which is of course an important piece of the puzzle, is how much does it cost to do the extraction? Because this is not all necessarily profit. We have to sort of figure this out. You have to understand what the demand is in the marketplace. So it's way more complicated than my back of the envelope calculation. But just when we start talking about tons of material, and some ratio of that is valuable at the milligram level, there's definitely some opportunity there. So this is the type of information that we're trying to unlock and shine a light on that has just been in the darkness for a very, very long time. This is just one chemical in one waste stream of one crop. Okay, so next steps. As I said before, we've done a deep dive on tomatoes, very deep dive on tomatoes. If you want to know anything about processing tomatoes, go ask Mariana over there. She knows everything at this point. We'll move on to wine grapes, almonds, pistachios, pomegranates, and others. We're trying to go through as many of these products as we possibly can. We recently got funding from the Resnick Agricultural Innovation Grant to continue this research. We certainly need to incorporate the cost of extraction data. We need to figure out how to integrate that into the database that we're building now, so that we can make have a bit more of a decision support system to understand, just because the value's there, is it worth getting it out? And I think that's a piece that we'll have to talk about with industry, but also it's an area for, it might not be cost effective now, but what if there's a new technology coming down the line? There's a really important link up to emerging technologies and the type of work we do here on campus, where we might uncover a new way to extract a particular compound, and we will instantly know how valuable that could be in applying it to some of these different byproducts. We also want to develop a user-friendly web portal to explore data. Some of our contacts who are going to help with that are in the room, so thank you guys. Looking forward to having you help us do that in the future. And then also we need to integrate some more AI components. This first round of tomatoes was very much a process by hand, just to build out the framework of what this needs to look like. What is the workflow of information? How does it all come together? But in this scale up, we need to start thinking about how we scrape some of this data more easily from the literature so that we can multiply our efforts beyond just the number of students in the lab. We also need to think about how is this going to be used down the line? What does this look like? Is it a website? And thinking about how can AI even help us unlock some of the knowledge in this data that we don't see immediately. So can we start thinking about how we might, use a large language model to prompt people when they, to develop prompts to explore the data to develop new solutions. All of this stuff is really interesting to me. Again, I'm an environmental scientist is my background, so I'm really looking forward to our partnership with the AIFS Institute to help think about how our problem and our data can be best leveraged by AI products that are, growing in their power and complexity every day, and thinking about how best we can put these two pieces together. One other piece I want to talk about is that all of this work does fit into the broader sort of ecosystem here at UC Davis. So, I do my work through food science and technology, but there's a number of folks that, and Harold mentioned this, at the Food Loss and Waste Collaborative that look at this issue from an economic lens, from a policy lens, you name it. You need to bring all this expertise together to start addressing this challenge. And so with that, I'll thank you all. Here's my lab. And here's all the different projects that we're currently working on. And this is really exciting work. It's my favorite project right now. Don't tell my other projects. But I'm looking forward to moving ahead in the future. I'm looking forward to your questions. So thank you so much.